Hi friends, today's lecture about PEB base plate design. Here we have I am मतलब हम जो है इसके अंदर इसके डिटेल भी देखने आते हैं. Okay, then we can proceed one example also, one complete example. In that we can see how can we design manually base plate design, base plate geometry. Now let's start. If you see the base plate generally used used for transfer load from column to pedestal. Okay, so if you see this is your column and this is our pedestal. Okay, if anything we don't consider at this joint, then this column will penetrate directly into this pedestal. That's why we use to transfer safely this column load to this pedestal. We use this we call as base plate. Okay, so this base plate can transfer the load uniformly to the pedestal. So this is concept we have used. So how can we this is base plate and pedestal we have transfer mechanism, we use this base plate. But actually if in this column suppose the load are coming and moments are coming, that moment this moment clockwise moment, anti-clockwise moment, if moment is coming in this pedestal, then our column or then this column uh, can behave or its ability to overturn this column with base plate. So that's why the second option we have used, that is we provide this base plate anchor bolt. Okay. Anchor bolt. Okay, this anchor bolt strengthening the this to the strengthening to base plate, and this anchor bolt can safely transfer all the moments and shear force uh, to this pedestal. Okay, and this anchor bolt have different shape: J bolt, U bolt, whatever the bolt we have considered. There is different types, so we don't go there. So let's see only this anchor bolt specification. This anchor bolts are can carry safely, transfer the load, and can carry only sometime compression, sometime tension according to moment. Suppose suppose in the moment consideration, if we consider the moment applied on structure, that moment are divided into two types. That moment are light moment. Light moment, it means the volume of the moment is very small, like 10 kilonewton meter, 5 kilonewton meter, 1 kilonewton meter. This is light moment. Okay. And second part is high moment. This that high moment is 50 kilonewton meter, 100 kilonewton meter, okay, 200 kilonewton meter. These are high moments. So these two types of moment are transferred to the structure. So if suppose these heavy moments, if light moment are coming into this pedestal column, okay, this this moment have ability to overturn this column, but in our in column we have used the base plate to resist lift forces and do not overturn. So that's why we use anchor bolt also to straining the base plate with column and pedestal. But if high moments come in our structure, then we have second option. If high moments will come in our structure, then we use stiffeners. Okay, these stiffeners we have used. So these stiffeners have this stiffener provide to the flanges with these stiffeners only connected with flanges, and this stiffener gives the base plate to carry high moments. So that's why we use stiffener with column. Okay. So basically these three types we have seen. There is no moment, only shear force with moment, light moment, and shear force with heavy moments. So these three conditions have actually very create differentiate in base plate design. Now we see how we deal with this with such type of problems. Now we have take some example with respect to IS code, then we can understand how we design this base plate. Okay, so let's begin. The base plate, given data we have considered the base plate size we don't know. The column size is ISHB 350 at the rate of 710.2 Newton per meter. Column carrying the load are first one factor axial compressive load, factor axial compressive load we have considered 1200 kilonewton. Second point, factor moment we have considered 150 kilonewton per kilonewton meter. Concrete grade of pedestal we generally use M30 and steel grade for base plate. that is FE410 or E250. Okay. Now the column section are in this ISHB 350. The column section is depth of section H is equal to 350 mm, flange width or B is equal to 250 mm, flange width 250 mm, depth of section 350, flange thickness are flange thickness TF is equal to 11.6 mm and web thickness TW is equal to 8.3 mm. So generally we have considered this type of column section for our column design example. In this we have used IS 800 2007. Okay, this is for general construction of steel, or IS 456 2000. This is for plain and reinforced concrete. The base plate and grout act together to transfer the load to the concrete pedestal. The critical section for bending in the base plate is at base of the column or wave. Okay. Now we have the start with this step one. Step one. In this step one, we generally use design of base plate dimension. Design of base plate dimension. Okay. In this base plate dimension, we need to find a plan. What is the length of our base plate and what is the width of our base plate? Okay. That's why we generally use permissible bearing stress on concrete. First step, first formula we use permissible bearing stress on concrete. Okay, that is clause 34.4 or IS 456 2000. This is permissible bearing stress on concrete. Now we have the formula for this uh, sigma BR, that is bearing stress of concrete, is equal to 0.45 FCK square root of A1 divided by A2. Okay, this under root of A1 divided by A2 basically we use for preliminary A1, because A1 is nothing but area of base plate. Okay, area of base plate, and A2 is nothing but the area of concrete pedestal. Basically, we consider the area of base plate is equal to the area of concrete pedestal. So that's why we consider this under root A1 divided by A2 is equal to 1 for preliminary calculation. So sigma BR is equal to 0.45 FCK into 1. Now 0.45 FCK we have used 30. Okay, the grade of concrete we use for this 30. So 45 into 30, we get, no, sorry, actually we consider here 2, the area, under root A1 divided by A2 we consider 2 volume. Okay, so this 0.45 into 30 into 2, we 27 megapascal. its maximum permissible stress value. If we consider under root A1 divided by A2 is equal to 2. Now we calculate in second step, determine base plate size. So for base plate size calculation, we have the axial load and the moment. Okay, and we have the formula eccentricity is equal to mu divided by pu. Here the mu we have given 150 into 10 to the power 6 and pu is 1200 into 10 to the power 3. Then we can get 125 eccentricity of load. Since this is equal to 125, is less than n by 6. Okay. Suppose in this base plate is under compression. We assume that base plate is in compression. There is compression, only compression will come in base plate or no tension zone in act. Now just let's go into the next point. Let us assume the base plate width. We have just assumed base plate width. So the base plate width we generally consider is B. Okay, B is equal to 400 mm because our column size is 350 mm. Okay, so space for welding or connection, so we can assume 50 space. So just we assume 400 we use for our base plate, column base plate size. One size we have given. Now the formula we have Pu is equal to 1 by 2 P max B into A3. Suppose we have used B is equal to 400. Okay. In this, we generally use we generally also go into this point, like suppose we have considered the other side where depth is equal to 650 just assume for trial method. Now n by 6 is equal to 650 divided by 6. This value come 108.3 okay, but our eccentricity is 125 okay, so this value is greater than 108.3 This means the part of the base plate is under tension. Okay, this means because n by 6 is greater than eccentricity. That means the part of base plate under tension. That's why we must use triangular pressure distribution with zero stress at one end. Okay. Now we go with second point. We generally consider triangular pressure distribution. In that, we consider this base plate and block. The pressure are distributed like this. Okay, so that's why the for E is equal to n by 6 maximum bearing pressure. So P max is equal to, we generally use the formula P max is equal to 2 into Pu divided by B into Y. Y is nothing but length of bearing zone in compression. Y is nothing but length of bearing zone. So this Y we get from n, Y is equal to 3 into n by 2 minus E. 3 into n by 2, it means we consider n is equal to 650 divided by 2 minus 125. Then we can get it's 600 mm. Y is equal to, okay. We put this value into the above equation. So 2 into Pu we get 1200 into 10 to the power 3 divided by B. We consider 400 into Y is 600. We get value 10 megapascal. Pmax value. Now this Pmax value are coming 10 megapascal and bearing stress value it's coming 27. So this value is less than 27 megapascal. Okay, sigma br. So it's okay if this Pmax value is less than the bearing stress value. Therefore, the base plate size we use B is equal to 400 mm, length is equal to N is equal to 650 mm, and bearing area is equal to 400 into 650. It should be 260,000 mm square. This is base plate we have calculated. Now we calculate the base plate thickness. So for base plate thickness, okay, just remember this procedure to find out the base plate size. Now this procedure will come. Now go into the next step, step 2. In step 2, the base plate thickness we find. The base plate thickness. For this base plate thickness, these are designed for bending caused by bearing pressure. From the concrete. The critical section are at column, flange and web. Here we consider the critical section are at the face of column and column, flange and web. Now let's start with the first formula, bearing pressure intensity. Bearing pressure intensity. For that formula, the factored bearing pressure is equal to W is equal to P max in is equal to 10 Newton per mm square. Or for cantilever projection, here we consider the cantilever projection. So projection beyond flange or projection beyond wave. So for that A, or for this B, we consider A is equal to B minus H divided by 2. Okay. So here B is 400, H is 350, column depth divided by 2. 400 minus 350 divided by 2. So here we get 25 mm. And for wave, n minus bf divided by 2. So n is we have 650, bf is 250 divided by 2. So it's 200 mm. So here B is more critical because the cantilever is more here to 200 mm. The projection B is more critical. Now, how can we handle this? So for that, the base plate is fixed. We consider moment calculation. So here we consider the base plate is fixed because eccentricity is very high and moment is very high, 150 mm. That's why we use this base plate is fixed, conservative, and the face of the column wave or flange. The bearing pressure is uniform under compression zone. For a conservative and simple design, we calculate the moment for 1 mm wide. Okay. For simple design, we consider moment of 1 mm wide strip. So for that, moment at critical section, the formula is m is equal to w b square by 2. Okay. W is nothing but 10 into b square by 2 means 200 square divided by 2. The value will come 2 into 10 to the power 5 Newton mm. Newton mm per mm because we consider one strip. Okay. This is moment at critical section. Now, from this moment, we calculate the thickness, the required thickness. For this required thickness, we have the clause 8.2.1.2 as 800 2007. The moment capacity of plate MD is equal to Fy divided by gamma m0 into Zp. Fy MD is equal to Fy in given data we have considered 250. Okay, and gamma m0 partial safety factor for this thickness calculation 1.1, and Zp plastic section modulus A for thickness of plate it's t square divided by 4. Now we calculate this value and the moment value for strip we have calculate this 2 into 10 to the power 5. 2 into 10 to the power 5. So just t square is equal to 2 1.1, okay, 1.1 into 4 into 2. This 4 into 8, 8.8 into 10 to the power 5 divided by 250. Okay, now into 10, it's 3520. T square is equal to t is equal to square root of 3520. It's 60 mm. Okay, it's very huge. 60 mm. Therefore, provide base plate thickness is equal to 60 mm. Here the base plate size will come, thickness will come 60 mm. So in this manual, we don't have assume the stiffeners also. So that's why we get this higher value. If we assume a stiffener also, so this stiffener can distribute the load properly, and if we design this anchor bolt also help to reduce this thickness. So that's why this base plate in manual calculation we get the base plate thickness is equal to 60 mm. If you want to accurately design or with respect to FEM finite element method basis, then we can directly uh, go with idea static or software also, or RAM connection. So this software help to reduce this effort of manual calculation. Second point, the grout thickness. Okay. The grout thickness. The grout thickness we use, the grout is a layer of high strength cement mortar used to level the base plate and ensure uniform bearing on concrete pedestal. Okay. The pedestal on this top of pedestal we use the grouting, or on this grouting this is thickness, and above this grouting we use this pedestal. Oh, base plate. This is base plate or this is grout. Okay. And according to I said, this actually used for uniform, to get uniform smoothness to base plate. This grout we use uniform bearing on concrete pedestal. IS 800 2007 does not specify the minimum thickness. It is specially specified in project specification. Okay, this IS 800 2007 does not provide any guideline about this thickness of grout. So we have generally used the grout thickness 25 mm to 50 mm. Okay, 25 mm to 50 mm, or whatever we want, we just take that value. In this example, we take 30 mm we use grout layer we use for our pedestal or base plate. Design of anchor bolt. If you want to design of anchor bolt, then design anchor bolts. Okay. For design of anchor bolt, here in above we see E is greater than n by 6. The base plate have tendency to uplift. If this value will come, it means the base plate have tendency to uplift. The anchor bolts are required to resist the tensile force. So that's why whatever we design, but for anchor bolt design, anchor bolt are required to resist tensile force. Now determine tensile force in anchor bolts. So let's start. Determine tensile force in anchor bolt. So from the force equilibrium in vertical direction, the total tension Tu is equal to Pu into E divided by Y. This is we have get from vertical equilibrium equation. Tu is equal to Pu into E divided by Y. Let's use the pressure diagram method. The compressive force C act at the centroid of triangular stress block. Now assume the pressure diagram. So we see the compressive force in that the triangular stress will have triangular force. The compressive force C acts at centroid of triangular stress block. The formula is for compressive force is equal to 1 by 2 P max into B into Y is equal to 1 by 2 P max is equal to 10, B is 400 or Y is equal to 600. So for that we get value 1200 kilonewton value for compressive stress. Now for to balance this, C must balance Pu and Tu. Okay. Now C is equal to Pu plus Tu. So C is 1200, Pu is 1200 plus Tu. So Tu is equal to 0. So it means this is incorrect because in our assumption we consider this is tensile force. Okay, the bolt carry the tensile force. So here the tensile force come is 0. So now we can recalculate this value. The line of action C is at distance y by 3 from H where stress is 0. Okay. Here suppose the stress is 0. From that point we calculate. Here stress is 0. Here stress is maximum. From this from to this y by 3 we for y by 3 value we calculate this line of action for compressive stress. So the formula we get C is equal to N by 2 minus Y by 3 minus TU into dt, depth into thickness. So here also uh, C into N by 2 minus Y by 3 minus TU into dt, okay, is equal to 0. This is equation 1. And second, C minus TU is equal to PU. Okay. C is equal to PU plus TU. That in this case, we put that value in leftward. C minus TU is equal to PU. So this is equation 2, where dt is the distance from column center to the anchor bolt. dt is here distance from column center to the anchor bolt. Typically n by 2 minus cover we use. Assume cover is equal to 50 mm to bolt center line. So dt is equal to 650 divided by 2 minus 50. The dt value will come to 75 mm. Now if we substitute this equation from this, then we can get pu plus tu into n by 2 minus y by 3 minus tu into dt is equal to 0. So this 1200 plus tu into n by 2 is 325 minus 600 divided by 2 minus tu into 275 is equal to 0. So if we solve this equation or this value, then we can get Tu is equal to 1000 kilonewton. This value we have get. So this is the total factor tensile force to be resisted by anchor bolt on tension side. So this force actually anchor bolt will carry. Now sizing the anchor bolt. So from this, how we calculate the sizing? Tensile, let's sizing the anchor bolts. Let's provide 4 anchor bolt. 2 on the tension side, so tensile force per bolt. Okay. Here 4 anchor bolt. So in our total 4 bolt we use. Let's suppose see this is our column. In this 4 bolt we use. So this 2 bolt carry compression and 2 bolt carry tension. So for that 2 bolt carry the tension. That's why we use tensile force per bolt. TB is equal to 1000 divided by 2 is equal to 500 kilonewton, because we consider 2 bolt carry tension and 2 bolt carry compression. Use tensile strength of bolt. Tensile strength of bolt CL is 10.3.5 in this clause IS 800 2007. In this, the tensile strength of bolt formula is given. T and B is equal to 0.9 into FUB into AN. It should be less than sigma YB into ASB into gamma M1 divided by gamma MB. So generally, the formula of TDB is equal to 0.9 into FUB AN divided by gamma MB. We use high strength bolts 8.8 grade. Suppose we use 8.8 grade bolt. Here we consider FUB is equal to 800 megapascal and FYB is equal to 640 megapascal and gamma MB is equal to 1.25. So here the AN is nothing but net tensile stress area. So for rough sizing, then we consider TDP is equal to 0.9 into 800 into pi by 4 into d square by 2 or d square into divided by 1.25. So here into is equal to 500 into 10 to the power 3. So here if we consider TDP is equal to 500 into 10 to the power 3 value, and our net strength value will become this, and here this only one unknown d square. So we put all the value here. D square is equal to 500 into 10 to the power 3 into 4 into 1.25 divided by 0.9 into 800 into pi. So we get D is equal to 29.4, 29.7 mm. So we consider D is equal to 30 mm diameter for grade 8.8 and the number of bolt is 4. So from this equation we have get the diameter and number of bolt for our anchor for our base plate. The anchor bolt embedment and projection. How much embedment, 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 anchor, bolt, embedment, and projection. How much it should be happen if we use 30 mm grade bolt. So this embedment length into the concrete pedestal should be sufficient to develop the bond strength and prevent cone failure. We have only two main focus. If we provide embedded length to the bolt, it prevent it bond strength with concrete, and second, it prevent cone failure. So these two points, if satisfied, then our embedded length is safe to structure. The column rule thumb rule we have considered for this embedded length 20 to 25 times diameter, 20 to 25 times into diameter of bolt. Here the L embedded we consider 25 into 30, we get value 750 mm. Okay, this 750 mm is sufficient. This is very long, often properly designed anchor bolt with a heavy base plate washer at end is used. For 30 mm bolt, a practical embedment of 500 to 600 mm is common, but it must be checked for pull-out capacity as per IS 456 or anchor bolt design guide. The projection, the bolt should be projected above the top of the base plate by about means this anchor bolt. Suppose this is pedestal and this is base plate. And here we provide the anchor bolt. Okay. So this anchor bolt should be projection above the top of the base plate. Top of the base plate. Okay. This is top of the base plate. From this to this above, we consider it should be 100 to 150 mm. To accommodate the nut and washer, provide we generally provide 120 mm. And this range 100 to 150 mm because we provide washer also for our fixity with base plate properly fixed. So here we calculate the base plate size, base plate thickness, grout thickness, anchor bolt, anchor bolt embedment, anchor bolt projections. So in this we have got all the detail according to IS code. Okay. So now I will give you some notes, important notes also. Here just write down important note. For important notes, the first one is for welding. Okay. In welding, the column must be connected to the base plate by full strength butt weld or fillet weld. This design is not shown here. Okay. Sometimes we use welding also to flange or wave for strengthen. So this point is not covered here. Second point, shear check. Okay, if you shear check in this case with no horizontal forces we consider. Okay, no horizontal force, only vertical force we consider. No horizontal force we consider. Shear is transferred by friction and bearing of the bolt. If significant horizontal force is present, shear key may be required. If horizontal force is coming into the structure, then we provide shear key. Now practical detailing, the base plate will have hole 35 mm diameter for anchor bolt. A washer plate is often welded under the nut. IS 800 2007 versus limit state method. This example use simplify working stress method for concrete bearing. A more accurate method using rigid plastic analysis of base plate is also permitted in IS 800. Okay, now this important note also I will give you, and we just see all the detail how we calculate the how we consider step one. We consider the base plate weight, then with respect to that weight we calculate the depth also, and from that depth we consider um, we consider the bearing stress also, okay, and the eccentricity, how much eccentricity will come in the structure, and base plate dimension we calculate base according to base plate dimension, then we can calculate the base plate thickness also. So this is step by step procedure, but what is the limitation in this? We cannot consider the horizontal forces or welding to the base plate. So in the next lecture we will cover that part also. So hope you enjoy this lecture. We will meet in next lecture.